Hey guys, welcome back to Trick Code. Today we're doing another Brainstellar Quant puzzle. This one is called Fruit Magic. It's a medium problem. You guys can go over the problem once. So first of all, let's define a few variables. So since in the question we've been given a certain amount of bananas, apples, and cherries, I'll call the number of apples as A, the number of bananas as B, and the number of cherries as C. And if you notice, then each point within the problem can be defined as a state where we have a certain set of A, comma B, comma C, right? So for example, the initial state is 13, comma 15, comma 17 because we have 13 apples, 15 bananas, and 17 cherries. So from now onwards, I'll be calling each point within the game a state, and I'll be denoting them by this triplet over here. So x comma y comma z. That's how state is going to look. So basically the question is that we've been given the initial state of 13, 15, 17, and we have to reach one of the three final accepted states, which look something like this over here. So each state basically denotes that we have all the 45 fruits of one particular kind. Over here, it's 45 apples. For this case, it's bananas. And for this case, it's 45 cherries, right? So we have to somehow start from this state and reach either of these three. And the only change in state that can happen is denoted by a transition. And what exactly is a transition? Well, a transition is basically a collision of two different fruit occurs, and both of them get converted to the third type. So they've also given us an example of an apple and a banana colliding to get two cherries, right? So what does this mean? So we can subtract one from any two and add two to the third, right? This can happen in any order. So over here, I subtracted a banana and a cherry, but I could also have subtracted one from apples and one from cherries and added two to the bananas, right? Get the point. There's three kinds of collisions that are possible. Now, if you start to try to solve this problem, you start to just play around with the numbers, and there'd be often times where you get really close to one of these three states, but you notice that you just can't quite reach there. And this is a pretty good indication that this problem, maybe the answer to this problem is that it is not possible to lead to all 45 roots of just one type. But if that is the case, then it's also important that we prove how that is impossible, right? Otherwise, the solution is incomplete. So, first of all, for these types of problems where we have to prove a certain case to be impossible, we have to start with the state and try to think about the properties about the state. So, what do I mean by that? I'm trying to hint you guys towards thinking of a property of the state that remains constant before and after transition. Well, for example, we could take the property of the state, and I'll denote that by a function of a comma b comma c to be the sum of a plus b plus c. If you notice the way the transitions work, the summation of a plus b plus c is always equal to 45. So I could say that this property of the state a comma b comma c, the property f of a comma b comma c, being this defined as this property of the sum of all three numbers, is constant and is always equal to 45. So essentially what I'm saying is f of a comma b comma c is always constant no matter what the actual state is at a value of 45. Looking at this, you might think, well, okay, so we initially had a sum of 45, and all the three ending cases also have a sum of 45. So according to this function or this property we just defined over here, it should be possible to start from this state and end at all of these three states, right? So this property that we defined over here of the sum of a plus b plus c is not really helping us here because it's leading to the solution that it is possible. But as we just discussed, that by trial and error, it seems that it's just not quite possible. So basically, if we can find an expression in terms of a, comma b, comma c that remains the same after any transition and has different values for the state 13, comma 15, comma 17 and 45, comma 0, comma 0. What I'm trying to say is, let's say I define a property f dash over a comma b comma c. F dash is a new property that I define, which has a different value for this state and a different value for this state, right? If I can come up with such a property f dash that has different values for the initial and final state, and I can also prove that this f dash property remains the same. The value of f dash remains the same after and before a transition. Then I could prove that since f dash remains same after any amount of transitions and it has a different value for the initial state and a different value for the final state, it is impossible to go from the initial state to the final state, because for that to happen, the value of f of dash would have to change from the value that it was at the initial to the value that it is at the final. But we also know that the value f dash does not change through a transition, and the only thing that we can do to change states is a transition. So hence we're proving that it's impossible to go from the initial to the final state. So another hint just before I tell you guys this solution, well, the expression or the function f dash of a comma b comma c that I'm talking about, it will be a linear combination of the three variables of a comma b comma c modulo 3. So this is the solution. This is the function over here, which I was talking about. Value of f of 13, 15, 17 is equal to 1, but the value of all these three final accepted states is equal to 0. The function remains constant during a collision. Try to add plus 2 to either of a comma b comma c and minus 1 from the other two, and you'd see that this expression of 0 times a plus 1 times b plus 2 times c whole moduloed by 3, this expression always remains the same no matter what kind of transition you try to do. And if all that we can do is these types of transitions, then that means that the value of f can never change. If we start with the value of f being 1, then we can never bring that value to 0. And this is how we prove that this particular arrangement would never be possible. So, to be very honest, I feel like this solution over here and the fact that you have to figure out this equation over here is not at all intuitive. So, I've also come up with another solution that, in my opinion, is a bit better. So, basically, how this one goes is that the end goal is to get a 45, 0, 0, right? And playing around with the numbers, you'd soon realize that what we actually want is, well, of course, first of all, we want any two to be 0, right? So if any two of the three numbers become 0, then automatically the third one is going to be 45, because as we just discussed, that the sum is always going to be equal to 45. So now if we want any two to become equal to 0, then by playing around, you also realize that what we actually want is for any two of them to be become equal, and the last can be whatever is left. So that would be just be 45 minus 2x, obviously. But the point is that we want any two of these three to become equal, right? Because if those two become equal, then we could just keep on minusing one from these two and adding them over to this one in order to make this one 0, 0 and 45 over here. So what we're doing is basically backtracking, right? So we want 45, 0, 0. We just deduce that. For that, we basically want two of them to be equal. So we want an x, 45, x, or any other permutation of these three values. Sorry, this is not 45, but rather 45 minus 2x. But focus on the two x's. So what I'm saying is that we need any two of the three variables to be equal. Now, what does equal mean? So that means that the difference or the delta between those two values has to be equal to 0. So if I call this as position 1, this as position 2, and this as position 3, what I mean is that I want delta 1 2 to be equal to 0, or delta 2 3 to be equal to 0, or delta 3 1 to be equal to 0, right? Where delta is basically the mod of the difference between those positions. Now, it's important to understand a point about the transitions, or the collisions rather. If you notice the collisions properly, so minus 1 comma minus 1 comma plus 2, right? This is how each collision looks like. You can notice that each of these three values, delta ij, to talk about in general, delta ij only changes by a value of 0 or 3 on any transition. Pause and think over this. So for any transition, the value of any delta changes by either a value of 0 or 3. Now, if we eventually want a delta value to be equal to 0, that means that we want a delta value to be equal to a multiple of 3, a proper multiple of 3, right? And now if we look at the initial state that we're given, which is 13, 15, 17, each delta is either equal to 2 or it's equal to 4. And these are not proper multiples of 3. And as we talked about earlier, that each transition changes the value of any delta, or rather all three deltas, by a proper multiple of 3. It either changes it by the value of 0 or 3, which is a proper multiple of 3, right? So 2 can become -1, or it could become 5. And similarly, 4 could become 1 or 7, but it can never become 0. 4 can never become 0, and neither could 2 ever become 0, because the values always change by a multiple of 3. And since we have an improper multiple of 3, because these values are 2 and 4, and we eventually want a value of 0, and the transitions only change the values of delta by a multiple of 3, we are never going to reach the final state from the initial state. So just to summarize what we just did, we backtracked the solution. So we knew that we had to have 45, 0, 0 and in the end. This led to us to deduce that we need x, x, 45 minus 2x, which means that we need a delta to be equal to 0, right? But all three initial deltas are, well, they're 2, 2, 4, and none of them is a proper multiple of 3. And each transition only changes the delta value by either 0 or 3. So none of these three values can ever become 0. So this proves that we can never go from the initial state to the final state. I hope you guys understood this solution too, and thanks for watching.